Hello, it's Keith here, and this is lesson 5 of my IBM370 assembly programming tutorials. So this is almost the last of the IBM370 series. The final one is only covering binary coded decimal and decimals. So if you don't care about that kind of thing, then I guess you don't need to watch that episode. So apart from that, this is the final episode in which we're going to look at the final few mathematics commands. I'm calling this power maths because it's basically things like multiplication, division, and then two of the commands that don't fit anywhere else, exec and test. Now, multiplication and division are relatively rare in assembly if you come from the 8-bit world where they don't exist. So that's why I've sort of left them until this stage. So that's what we've got today. You could skip this lesson. I'd suggest you don't. But then, as I say, after that, we're looking at, in lesson 6, we'll be looking at the incredibly powerful binary coded decimal commands, or just decimal as it calls it. Very, very powerful. So extremely impressive. It contains the most advanced assembly command I've ever seen. The decimal on IBM370, absolutely amazing. Anyway, that's not what we're looking at today. So first of all, let's make a start. And let's get our simulator emulator started up. I always change the hello world message just so we can check it's really started. So let's change it to I like maths this time, because we're going to do maths, so we'd better enjoy it, even if I personally am not very good at it. So we select the Hercules job because we're running an entire JCL file here. Let's fire that up. Our server is starting over here. It's off screen. I need to leave it alone though because there's some send key scripts to get everything set up. Okay, it's running away, and our screen at the far right, the printer output, should show the results any moment now. This will show the results. I can see it coming up on our terminal. There it is. There's the results. And somewhere here, I like maths. So that shows that we've run that script okay. So our server is started. That's our terminal window. We don't need to look at that. That's our server window. We don't need to look at that. We'll just leave them off screen there. Okay, so now let's run this example, lesson 5. So we'll fire this up. We don't use Hercules job. We use this basic job with the header and footer, because the header and footer include a job header and also the scripts that I use for things like dumping registers to the screen, which is things we want to do. Okay, so let's take a look at our multiplication test here. So we're using the multiply command here. This will multiply a register by a memory address in another register, and using an offset R0 being a hardwired 0 here. Now, this command, actually, like quite a few of the commands, is actually 64 bits. So the result is 64 bits, but we don't specify a pair of registers as the destination. What we actually do is we specify just the first of the registers, and the second is implied. So we're specifying R0 as the destination here, but that will imply R0 and the following register R1 here. So R0 and R1 are the 64-bit result. Now, the source of the multiplication isn't actually R0. It's only a 32-bit value, but it's actually R1. You can see here we've loaded R0 with the value 0 and R1 with this test value here of 1000. And as I say, the 64-bit result is in R0 and R1, but the 32-bit source is not the R0 that we specified. It's the low part R1. Little bit strange there, but anyway, so we're multiplying by R3 here, the address in R3, which is hex value 1. Now we can see hex value 1 all the way down here, and it's this quadruple 6, quadruple 3 value here, which when we multiply by 1000 should give a nice clear result. Okay, so here is our starting position here. You can see R0 contains all zeros and R1 contains 1000. You can see the memory address here with the value that we're effectively multiplying by, this 32-bit value here. And the result you can see on this second line here. So the 64-bit value does indeed contain R1 multiplied by the memory address here. So that has worked as we would kind of expect. Now, one thing I should point out, I've been a bit excessive specifying R0 here. We can actually remove it, and this assembler will assemble just fine. And if we just change the value here, we move that 0 along 1 and we run again, we'll see that this runs fine without that R0 specified there. The R0, of course, hardwired 0, so it has no effect. And so you can see this time, we're now multiplying by 1 and 4 zeros, and the result is there. So this is assembled just fine with that. Without that specified R0 there. You can put it in if you want, but the assembler will put it in for us automatically. So no, just make it clear that that's an optional thing. Okay, So that's the multiply command for multiplying two 32-bit numbers and giving a 64-bit result. We do have another option though, multiply half. So the result this time is in just a single register, and it multiplies the 32-bit value in that source register by a 16-bit value in memory here. So this time what we're going to do is we're going to load these two test values into R0 and R1, and we're going to multiply these by these halves at offsets 4 and offset 6 to memory address R3. Now R3 contains hex value 1 still, and so we'll be able to see these results. So let's take a peek at what actually happened here. Okay, so you can see here R0 and R1 contain those test values there. Now at memory address offset 4, you can see that will be this 16-bit value just here, and so that has been multiplied, and you can see that 1, 2, 3, 4 has indeed been multiplied by R0 and then the result stored in R0, and that is because of that command there. The second one, well, that will multiply by this value here and multiply R1, so you can see FF0 has been multiplied by 1 quadruple 0 there, and that's stored in R1 as a result of that command there. Now in those cases we've been multiplying by memory addresses and registers, but like with a lot of commands on the IBM370, if we add an R to the end, we can actually multiply a register by a register here. Now this again will store a 64-bit result as a result of multiplying two 32-bit values. So when we specify R0 here, we're actually multiplying the value in R1 and storing the result in R0 and R1. However, when it comes to R3, it's actually just R3 being used. So R1 is the 32-bit source, R3 is the 32-bit parameter, and R0 and R1 are the 64-bit destination. It's a little bit confusing. I do understand why it does it like this, but it's a bit weird. You're specifying R0, but R0 isn't actually one of the source parts of the multiplication. It's only the first part of the destination. But that's the way it is, so that's what we have to work with. Okay, so we've loaded R1 with this test value here. We've loaded R3 with this test value here. And we've done our multiplication. Now, this is effectively a signed number. So when we've done our our multiplication, it has sort of filled all of the extra bits with ones there. So we can see lots of F's there. And then you can see F, E, D, CBA 98 there because of the multiplication of those two values there by this command here. So very straightforward. A very powerful multiplication there. I mean, personally, when I'm doing assembly, I usually do 8-bit systems, and so those you don't even have multiplication commands at all. And you know, you often branch out into 16 bits for addresses. You may even go into 32 bits, but the thought of 64-bit multiplication is just some crazy dream world that we can barely imagine. So yeah, it's very, very powerful. But of course, the IBM370 was a sort of mini computer, mainframe supercomputer kind of thing in the 70s. So it's not surprising that it is capable of extremely capable mathematics of significant precision. And 64 bits is still significant precision today, and this was doing this 40 years ago or more. So very, very impressive. Anyway, that's the multiplication. We also have division. Now, in a reverse of the multiplication, the division takes a 64-bit parameter, divides by a 32-bit parameter, and gives a 32-bit result, but it gives the result in two parts. Now, the first part is the whole number result, and the second part is the remainder. So it's using two registers as the result, but it's only a 32-bit whole number result of the division. So there we go. So what are we going to do? Well, what we're going to do is we're going to load a 4-bit value here, 1, 2, 3, 4, 5, 6, 7, 8, 9, A here, and we're going to divide that by another value. Now we're going to use hex value 2 here, and we can see that somewhere down here. Here's hex value 2, so 1 quadruple 0, and we'll show that to the screen as well. So let's just fire this example up. Okay, so we're doing our division here, and we're specifying R0 here, but of course R0 specifies a pair of source registers, so a 64-bit pair, R0 and R1, and the division will then be performed by the memory specified, which is R3 offset by hardwired R0, so just 0, and with a numeric offset of 0 there. So that's just effectively all the address in R3, and then we are going to store that result in R0 and R1, but R0 will contain the remainder, so the integer remainder, and R1 will contain the result of the division. So let's see that on the screen here. So we got 1, 2, 3, 4, 5, 6, 7, 8, 9A here. We divided by this value here, this 1 quadruple 0 here, and our result, the whole number part, is 1, 2, 3, 4, 5, 6 here, and the remainder is 7, 8, 9A here. So you can see that that is the result of dividing that 64-bit number by that 32-bit value in memory, and we get a remainder and a result there. Okay, so that is working memory to memory. We can also work with a pair of registers. So here we're specifying a source register, here we're specifying R0, but once again this is the first of a 64-bit pair. So when we specify this, we're actually specifying R0 and R1 as a 64-bit pair. So again, 1, 2, 3, 4, 5, 6, 7, 8, 9A here. This time though, the second parameter, the 32-bit parameter, is a register. So we've got the same value in the register just here. Actually, that's not the same value. It's got an extra 0, so that's 1 and 5 zeros. So extra bonus 0 there. So we're going to do that, and then again, just like before, the result is in 2 registers. R0 will contain the remainder, and R1 will contain the actual result of the division there. And you can see here on this second line down here, we have got our test value here, 1, 2, 3, 4, 5, 6, 7, 8, 9A here, and we've divided by that huge number in R3 there. And the result is 1, 2, 3, 4, 5. That is the whole number result. The remainder is 6, 7, 8, 9A here. So that is the part that was left over after that division by R3. So there we go. So very capable. There's no commands for dividing by halves to my knowledge. So there's no equivalent of multiply by half there. But again, extremely powerful capabilities there. Very impressive. So again, it's so far more than I'm used to with assembly, coming from the 8-bit world, that you just left wondering what you'd use them for. As I say, 64-bit multiplication and division for writing little games in Z80 is just unimaginable. But as I say, the IBM370 was designed as a sort of power computer, so it will have been doing things like accounting and financials. It'll have been running simulations and things, so. Yeah, very obvious why they would need that kind of capability. Anyway, that's multiplication and division away. Now what we're going to do is we're going to look at some of the weirder commands that really don't fit anywhere else. So the first of these, we're going to look at the exec command. This is a fascinating command. Now what this does is we specify a memory address, a MICOM in this case, and there is a single command at this address. And what we can do is we can execute that command out of, as a sort of one-time thing. So this isn't like branching to a subroutine and returning. This is just executing that one command without any kind of branches. Okay, so that sounds pretty straightforward, but there's an extra trick to it. We specify a single register here, and what actually happens is the command at this address will be loaded into the processor, and then the bytes of that command will be ORed with the value within the register we specify. Now this doesn't change the memory address at MICOM. It's just a sort of one-time thing, and so depending on what we put in R3, the actual command that's executed will be potentially be different. Now in this first case, I've loaded it all with zeros, so it won't be different. But if we put something else in there, which we will do, we will get different results. Now, how do we know what those results are? Well, I'm afraid you're actually going to have to get the IBM370 handbook out and look at the instruction set and how the bits affect those commands, because every command is different. Remember my addressing tutorial, the commands were in different sections. That defines the bit layout of the different commands. So anyway, so what have we done here? Well, our test command here is effectively adding 1 0 to register R0 here. Now at the start here, register R0 contained F and a load of zeros. You can see it just here. And then our first iteration ran my command with a byte that effectively will be ORed with that command of 0. So that makes no change to the command. And so when we ran, we went from the value here to the value F and then 5 zeros and then 1 0 there, because we ran that command as is. Now, what we did the next time we ran my command with the execute command, though, is we changed the value in R3 and we changed it to 1 0. Now, because I know what the layout of that command is, I know that that will effectively alter the register specified with this add command. And so this byte sequence here, when ORed with that command, will effectively change this command, and instead of changing R0, the next time we run it, it actually changed R1, because that byte sequence there is changing the register number. And as I say, it's changing it only at this execution. It's not changing the memory address MyCom. So this command is still the same command for when we change it again the next time. So this time we're changing to 20 and we're running again, and this effectively changes us to use register R2 here. And so you can see here, the next time we've run, R1 hasn't been changed, but R2 has been changed here. Now, it's all very clever. The final execution here, we've used register R0. Now, like with a few other cases, R0 is a hardwired 0 in this case. So even though R0 contains this crazy value here, when we do that final execution of the mycom command with EX here, that hardwired 0 has no effect. So the original command here is run again, and R0 is changed here. And again, that makes the point that the actual command here was not changed by these executions here. Now, why would you want to do this? Well, I mean, this is kind of like a more advanced version of self-modifying code, I suppose. Self-modifying code is where you reprogram the code in memory. It's a trick used in 8-bit programming quite a lot to gain speed. But this is something a bit different. As I say, it's a very powerful command that you might not need in a lot of cases, but you know, maybe there were very good cases you would want to do this. And as I say, it's simply something that most processors would never offer. Very, very interesting, very impressive command. Okay, we barely scratched the surface with the IBM370's very impressive commands, though, because now we have another very impressive command. Now, this is going to be using a lookup table. Now, this is actually something you do see from time to time. Other processors have similar things. What this is going to do is it's going to take a lookup table. It actually takes a pair of memory addresses. Now, it takes a byte specification, a lookup table, and a destination. And what this is effectively saying is it's saying change the L bytes, the memory address specified by the destination, using the lookup table specified by the second parameter here. So in this case, I'm using this syntax here, which is just an alternate version of this using labels. So what we're saying is use the bytes at my lookup table, my LUT, and change the 8 bytes at my data accordingly. Now, what this basically does is it goes to each of these bytes at my data, and it uses these numbers as an offset at the data at my LUT, and then it will read the equivalent. So this would take the value at 1, that's that byte there, and it will write it back into the source data here. Now, the lookup table here, in theory, might need to be 256 bytes, just depending on the data in my data. But I've only used values up to 6, so we don't need to worry about that. So let's just fire this up and let's see this in action. I think I'd already run it. Anyway, let's see the result of this. Okay, so here is the initial starting position. This first line is the lookup table. This first line is the source data. This second line is the lookup table. And then we are running this translate command. We're translating the 8 bytes at my data with my lookup table. And you can see afterwards here, well, 1 has been converted to A, 2 has been converted to B, 6 and 5 have been converted to F and E. That other 5 there has also been converted to E. The 6 and 6 have been converted to F and F. So we've converted this line here with this data here. Well, why would you want to do that? Well, there's a whole wealth of reasons why you might want to do this. You could use this in graphics. You'd use it maybe for color conversion, but I mean in terms of the IBM370, maybe you want to use it to convert that rotten EBDIC into ASCII or something like that. Yeah, as I say, there's a whole wide range of reasons you might want to do this for converting one format of data to another. And as I say, very, very, very capable command that a lot of systems simply can't offer. Of course, you can do this with a loop as well, but again, the IBM370 has this command that will do it for us. So yeah, if you want to translate data in memory, that's the kind of command you might want to use it for. The IBM goes even further though with this absolutely crazy command, I can't initially think of a reason exactly I'd want to do this. This is the kind of thing you might use if you were writing virtual machines and things. But what this basically does is it takes two parameters. One is a memory address and the other is a lookup table. However, this one doesn't change the source data. What it does is it compares the offsets with the source data, looks at the offsets in the lookup table, and it looks for a byte that isn't a 0. Now this effectively, as I say, if you were looking, maybe you're looking to scan a table for a particular kind of result, again, maybe you've got all kinds of numbers and you want to find the first ASCII character. Well, you could use this to ignore those numbers and only consider those ASCII characters. So again, we've got our data here with 1, 2, 3, 4, 5, 6, and 3 and 0. And then we've got these entries here. Now this entry would be 0, this entry would be entry 1, and this entry would be entry 2, and this entry would be entry 3. And as I say, what the translate command does is it will look at each of the bytes at the source specified memory address, and then it will compare those offsets within the lookup table and will try and find and see if they're 0. And it will set the condition codes accordingly. Now, it will return a value of 0 if all of the bytes that were tested returned a 0 entry in the lookup table. It will return a 1 if a non-zero was found. It will return a 2 if the last byte was non-zero but all of the other bytes were checked. Now, as if that wasn't crazy enough, this command actually does some things that we might not expect. As well as setting the condition codes, this actually uses some specifically numbered hardwired registers as parts of its result. Now, in our case here, we're specifying R3 as the register we're using for the source data, but this command will, whether we ask it to or not, use R1 and R2 as well. Even if we used R1 and R2, it would replace them. So basically, R1 will be set to the address of the byte in the source data at the point that it ends. At least 24 bits of it will, and that's because the original systems had 24-bit addressing. And then finally, R2, the 8 least significant bits, are set to the non-zero lookup value that was found as part of this scan. Okay, so let's see what actually happens when we run this command. So we're loading R3 with my data 2 here, and then we're going to do the scan here, and we're going to scan using my LUT2 here. Now what's effectively going to happen is it's going to scan this byte and it's going to find that match, so that's a 0. Then it's going to find this byte and then it's going to find that match, which is a 0. And then it's going to find this byte here, and that's going to be this here, which is a AA, which obviously is not 0, and at that point it's going to abort. Now we can test that theory, but we can see the results of that theory, should I say. So basically, as I say, the 8 bits of R2 will be set to the non-zero LUT value. Now, at the start of our execution here, R2 was loaded with all those Fs there, and you can see here after that first execution, it's been loaded with that AA value here. Now, R1 will be loaded with the final address here, or at least the 24 bits will. So it contains 95C5E here. Now, you can see this is C, D, and then E here. And so that has basically pointed to that value there. Now, in the case here, the only slight problem we've got here is this top byte actually contains FF, because as I say, it only sets the bottom 24 bits. Now, I think actually that is technically okay on this system. I don't think this system's using full 32-bit addressing. But just for safety, what we're going to do here is we're actually going to reset the value R1 with our original source address, and then we're going to run the test again. So this time, the second time, our top byte is actually the correct memory address for the current running position, so that's been loaded with 00. But of course the results, because we've done the exact same test there, the results were the same. But this now gives us the advantage that once we've run that test the first time, we can now effectively add 1 to the memory address in R1, move past that first byte that we found that was non-zero, and we can continue the test. So we're now continuing the test another time here. So we were pointing to this value of 3 here, which was pointing to this A. And now what we're going to do is we're going to test again. Well, we'll hit this 4, and that points to the value B. And you can see here, the next line, we've loaded the value B, and you can see our destination address in R1 has gone up by 1. Okay, well, let's run the test again. Let's move to the next byte. Let's run the test, continue running that test. Well, this time we're going to be comparing this 5. Well, that is the value 0 in this entry table. Then we'll continue testing for 6. We'll get this 0 here, and then we'll get this 3, and of course that points to this A here. And so we will then get this value of A here, and we'll get that result there, again with the condition codes of 1. Now, just for completion, we will continue the test again. We'll test again using MyLut2. And so here we're running again, but this time we didn't find any matching bytes that weren't a 0. So the final condition code is 0, and that means that all the bytes were processed and no match was found. So it's an extremely powerful command that, as I say, it's simply not the kind of thing you would generally need. But if you were writing, as I say, if you were writing a piece of code like a virtual machine, like a string scanning piece of code that only wanted to find certain results, very powerful, just provided you have enough memory to store a 256-byte, up to 256-byte lookup table. Anyway, there we go. So that's all we're covering this time, and we've covered everything now on this processor, I believe, except for the binary coded decimal, or so-called decimal commands. So you know, I don't know. This is such an old system. I'm not sure what the average viewer of it is doing. If you're just looking at it for curiosity, but I mean, if you were going to go out and go programming your IBM370, you could generally do that now. But I would suggest you stick around for the decimal tutorial as well, because it's very interesting. The binary coded decimal works slightly differently to a lot of other systems, and it has a ton of extremely powerful commands. So it's very, very impressive. Anyway, I hope you've enjoyed what you've seen today. Thanks for watching, and goodbye.